All right, welcome to episode 3.2. Let's jump straight into this explainer, because today we are completely tearing down the wall between abstract electrical theory and the heavy, spinning iron of a marine power plant. We're going to demystify exactly how frequency and voltage actually get controlled on a ship. Look, when you stare at a switchboard, it's super easy to just see a bunch of numbers glowing on a digital screen. But those numbers, they represent a highly coordinated, incredibly dynamic, mechanical and electrical ballet that keeps the entire vessel alive. So we're going to break down the two main control loops doing all the heavy lifting for us.
Now, I really want you to burn this concept into your mind right off the bat. Network frequency isn't just some arbitrary electrical value floating around in the wires. No, it is a direct physical mirror of exactly how fast your diesel engines are spinning, literally moment by moment. When you look up and see 50 hertz or 60 hertz on a meter, you are looking at engine speed made visible. It's really that simple. If the frequency drops, your massive steel engines are physically slowing down under the load.
Section 1. Governing active power.
So before we can talk about the whole power plant, we have to understand active power. Active power is the actual physical heavy lifting being done by the system, pushing the ship through the water or running the heavy deck machinery. And as we just established, controlling that comes down to controlling the speed of those engines. Here's how that physical chain of command actually plays out. We start with the governor, which is running a PID controller. That stands for proportional integral derivative, but honestly, you can just think of it as a relentless high-speed calculator that's constantly correcting the engine speed. This governor sends a speed reference signal to step 2, the electro-hydraulic actuator. And this isn't just sending some digital ping. This actuator physically, mechanically pushes the fuel rack in step 3. It literally injects more or less fuel right to the cylinders. And that brings us to step 4. The resulting network frequency. So governor to actuator to fuel rack to frequency. That is your continuous physical loop for active power.
Section 2. Governing reactive power.
Now, active power is really only half the story in a marine electrical network, right? We have to run a parallel track. Governing reactive power manages the current that actually magnetizes your motors and transformers so they can function, even though it doesn't do the physical work itself. And this whole side of things, it's all about voltage control. Unlike the physical fuel rack we just looked at, controlling reactive power is purely electrical. Here, an automatic voltage regulator, or the AVR, controls the network voltage by directly modulating the synchronous generator's excitation current. It's actually a very elegant relationship. You pump more excitation current into the generator's rotor, you get more voltage out on the network. If the voltage gets a little too high, the AVR just pulls that excitation current right back. Let's put these two loops side by side really quick, because this comparison absolutely locks the whole concept into place. On the left side, we have the governor loop. It controls active power by physically moving a fuel rack to manage engine speed. On the right, we have the AVR loop. It controls reactive power by electrically modulating the excitation field to manage voltage. One is basically a mechanical muscle, and the other is an electrical magnetic field. But the key here is they are operating simultaneously, side by side, every single second that ship is running to keep the power plant perfectly stable. Section 3. The 95% rule. But hey, what happens when things go completely sideways and the system gets pushed to its absolute limits? Well, we rely on a critical constraint that every single marine engineer absolutely must know to protect the physical generator from literally destroying itself from the inside out. And that entire constraint comes down to one single crucial number: 95%. This is the 95% of nominal frequency knee point. It's not just a guideline, it is a hard and fast survival rule that's hardwired directly into the system. So what exactly happens at this 95% threshold? It triggers what is called under-frequency voltage roll-off. Here's the worst-case scenario. Say the engine is bogged down by a massive load, and its speed, and therefore the network frequency, drops below 95% of its normal rating. The AVR automatically steps in and forces the voltage reference down. But why? Well, because when a generator is running slow, its internal cooling fans are also running slow. If the AVR kept stubbornly trying to pump maximum excitation current into that rotor to keep the voltage up while the machine is struggling and poorly cooled, the generator would severely overheat. It would sustain massive thermal damage. So rolling the voltage down protects the machine from basically cooking its own windings. Okay, let's put you in the hot seat for a second with a quick interactive stress test. Imagine you're standing in the engine control room. Suddenly, bam, there's a massive heavy load surge on the network. You look up at the meters and the network frequency sags all the way down to 92% of its nominal value. Based on the rule we literally just covered, What should the AVR automatically do to the voltage reference right at that exact moment? And exactly why should it do it?
If you immediately thought decrease it, you absolutely hit the nail on the head. Because 92% is firmly below that 95% knee point, the AVR has to automatically roll the voltage reference down. It totally abandons trying to hold the perfect voltage in order to save the generator from overheating due to overexcitation, especially while it's already running slow and super vulnerable. It's literally a built-in survival instinct for the hardware.
So let's synthesize all of this into one single, unified view of a stable power plant. You now know exactly how this dynamic works for a single generator. The PID governor is out there driving the physical fuel rack to maintain your frequency and your active power. The AVR is simultaneously driving the excitation current to maintain your voltage and reactive power. And standing guard over both of them is that 95% knee point rule, fully ready to step in and sacrifice voltage to protect your incredibly expensive generator hardware from thermal destruction if the whole system gets dragged down. Now, everything we've looked at today brilliantly explains how one isolated generator controls its own frequency and voltage. But here is a somewhat provocative thought to leave you with. Marine vessels almost never rely on just a single generator. They run multiple machines in parallel, all dumped onto a single shared busbar. So if every single generator is stubbornly trying to control its own frequency and voltage, what stops them from just fighting each other for the load? How on earth do you make sure every generator carries its fair share without dragging the others down? Well, that massive puzzle is exactly what we're going to unravel in our next explainer on load-sharing methodologies. You definitely won't want to miss how they solve that one. Catch you next time.